quiet of the Martian night, when the thin atmosphere lets the stars burn with an intensity unknown to Earth, a peculiar shadow crossed the red world's gaze. Against the darkness, a visitor shimmered. Three-Eye Atlas, a body not born of our sun, a fragment of the interstellar deep, now caught for a fleeting instant in the mechanical eye of Mars's orbiters. The first images that arrived were not simply photographs. They were riddles etched in light. At first glance, they resembled any cometary speck, a pale blot uncertain against a backdrop of stars. But when processed frame by frame, the light did not behave. Its pulse was erratic, like the heartbeat of a creature unfamiliar with the rhythm of this solar system. Instruments circling Mars had been directed toward the heavens, expecting to find only silence and dust. Instead, their detectors found reflections, sharp glints at strange intervals, as though surfaces were turning deliberately toward the sun. Shadows, too long for the object's presumed size, stretched across the imaging field, suggesting structures, not randomness. And within the thermal maps, heat seemed to rise and fall out of cadence with the sunlight, as though the body obeyed laws that our physics had not yet written. This anomaly, captured in the stark clarity of the Martian sky, would challenge the fundamental tenets of celestial mechanics. If you want to be the first to know when the universe reveals its deepest secrets, you need to be part of this community. Subscribe now. Hit that bell so you never miss a discovery. The cosmos is calling. Answer it with us. Mars had become the second great eye of humanity. From Earth, we had initially seen Three-Eye Atlas as a faint intruder, slipping in and out of awareness, a whisper against the galactic hum. But from Mars, strategically closer in geometry, the visitor looked stranger, clearer, and far more unsettling. The planet's orbital alignment had placed it in a perfect position to watch the interstellar body's trajectory and physical properties unfold. And in that vantage, something entirely unexpected was revealed. It was not simply a rock, nor quite a comet, nor entirely a conventional asteroid. It was an interloper, carrying its own intrinsic geometry, its own kinetic behavior, and its own unsettling message from the spaces between stars. With each pixel recorded, with each glint unraveled into precise telemetry, Mars did not just see a fragment of the void. It amplified a profound scientific question. This question was sharp enough to pierce the foundations of planetary science and vast enough to whisper of other worlds, other times, and perhaps physical processes that lay entirely outside human experience. The red world stared into the dark, and the dark, magnified through the anomalies of Three-Eye Atlas, seemed to stare back. The scientific journey of Three-Eye Atlas began not on Mars, but in the patient, sleepless nights of astronomers scanning the skies from Earth. Telescopes designed for continuous watchfulness, notably the ATLAS, Asteroid Terrestrial Impact Last Alert System, swept the heavens in search of subtle motions. When Atlas first caught the faint streak, it was initially cataloged as a distant wanderer. However, subsequent orbital refinement by global teams quickly confirmed its profound distinction. The calculated orbit could not be closed. The object's velocity, precisely plotted against the sun's gravitational influence, showed a clear positive hyperbolic excess velocity, the undeniable signature of an object unbound to the solar system. Unlike periodic comets, which are gravitationally captive, Three-Eye Atlas was a true interstellar trajectory, much like its predecessors, Oumuamua, Borisov. It was not a product of our sun. It belonged to the Milky Way galaxy. The announcement generated a quiet shockwave across observatories worldwide. Humanity was once again offered a fleeting chance to study matter formed under alien suns. What made this encounter unique, however, was the geometrical alignment. As 3I Atlas curved inward, Mars was perfectly positioned to provide a complementary, high-resolution view. Earth was awkwardly aligned, viewing the object against crowded star fields, with resolution limits stretched by distance and atmospheric distortion. Mars, acting as an advanced celestial observatory, was poised to capture details that would be fundamentally unattainable from Earth's surface. The recognition marked a moment of historical and operational significance. Astronomers had spent generations laboring under the assumption that interstellar objects would remain theoretical. Yet, this third confirmed visitor, 3I Atlas, forced an unprecedented two-world collaborative stage. Earth-based telescopes provided the initial detection and coarse astrometry, passing precise coordinates to the deep space orbiters at Mars. Data flowed through the vacuum, a shared pursuit across two planets separated by millions of kilometers. This was a triumph of distributed scientific engineering. The individuals driving this pursuit, graduate students meticulously analyzing digital images, data analysts feeding coordinates into complex orbital models, and engineers recalibrating detectors for an unexpected target, were the unsung heroes who opened a window onto the interstellar deep. Their tools, primarily designed for planetary defense and Martian geology, had instead become the eyes for tracing a profound cosmic stranger. This discovery phase, transitioning from initial faint anomaly to confirmed galactic messenger, set the stage for the true mystery to unfold on and around Mars. Mars was deliberately chosen as the optimal secondary viewing platform. Its thin atmosphere and high orbital altitude grant a clarity to the void that is almost clinical, a visual environment free from the dense, refracting blue haze of Earth. The red planet, a frozen plateau adrift in space, allowed its orbiting machinery to view the void as sharper, colder, and more absolute. When 3I Atlas entered the critical phase angle relative to Mars, scientists knew the red planet would provide the unique observational geometry required. The operational decision was highly strategic. Earth's network of observatories, while powerful, is inherently bound by weather and atmospheric turbulence. Mars, however, carried a sophisticated pre-existing flotilla of resilient machines ready for immediate retasking. Individually, each instrument was built with a focused Martian objective. Collectively, through rapid, coordinated retasking, they became the most advanced interstellar observatory ever conceived. The geometric advantage was paramount. As 3I Atlas curved across its solar system trajectory, Earth was forced to view the object primarily at low phase angles, where the observer is nearly looking straight at the object's sunlit face, leading to crowded starfields and blurred edges. Mars, however, was offset just enough to view the object at extremely high phase angles, where the object is seen nearly edge-on against the sun. This vantage allowed its orbiters to capture details Earth could never: sharper light-scattering profiles, richer thermal contrasts, and a unique perspective on the object's rotation and shape. Mars did not merely watch an object pass. It caught the body in a critical, revealing pose. Philosophically, utilizing Mars was a break from the singularity of Earth-centric cosmic observation. For centuries, our knowledge was filtered through a single planetary lens. Here, two planets, one pulsing with human intellect and the other humming with robotic precision, worked in concert to interrogate an interstellar ghost. It was a symphony of geometry and cutting-edge technology, a truly borderless act of planetary cooperation. As the first packets of light curves, thermal maps, and spectral lines flowed, they carried not just measurements, but the profound weight of this dual-world expectation. Mars, the silent, cruel observer, had become the witness the universe required. The imaging campaign was a tapestry woven from multiple coordinated orbital instruments. MRO's high-rise camera, normally tasked with peering into Martian gullies and dune fields, was commanded to focus its exceptionally high-resolution optics, capable of resolving objects down to 30 centimeters on the Martian surface, onto a target far smaller and vastly more elusive than any crater. Its resolution was used to measure the faint sub-arcsecond pinprick of the Wanderer, attempting to capture the minutest changes in shape and orientation. Complementing this, CTX provided the necessary wider field context, capturing surrounding star fields essential for anchoring the astrometric measurements, providing positional data accurate to within a few kilometers. The visible spectrum was only the beginning. THEMIS, the thermal emission imaging system, was tasked with following the thermodynamic pulse of 3I Atlas. Its mid-infrared eyes monitored the body's surface temperatures, revealing its thermal inertia, the rate at which it absorbs and releases heat. A compact, dense body shows one thermal signature, a fragile, porous structure shows another, and a thin, sheet-like structure shows a third. The resulting temperature curves were the key to reading the visitor's material character. In the non-visible spectrum, the ExoMars Trace Gas Orbiter became critical. Its NOMAD and ACS spectrometers, initially designed to search for trace gases like methane in Mars's atmosphere, were briefly retuned to stare at the interstellar body. This allowed them to capture absorption and emission lines, hinting at the molecular compounds, particularly any outgassing volatiles surrounding the object. Simultaneously, MAVEN, a spacecraft dedicated to studying the interaction between the solar wind and Mars's atmosphere, found itself listening for the faint plasma signature stirred up as the high-energy solar particles washed over 3I Atlas. This was less improvisation and more high-stakes orchestration. Commands were written, triple-checked, and uploaded across agencies, NASA, ESA, JAXA, to ensure each spacecraft maneuvered into the perfect position. It was a delicate, high-speed ballet. Orbiters hurtling through Mars's sky, timed so their detectors would open their shutters in unison, capturing photons that had left the interstellar traveler only moments before. For the first time, an interstellar body was interrogated across the full spectrum from the unique vantage of another planet. The instruments, fused into one powerful observational system, were the orchestra and the baffling celestial mechanics of 3I Atlas was their score. The initial light curve streams appeared standard, brightness plotted against time. However, as the hours passed, the data utterly refused the simple, predictable shapes expected from a rotating body. Where a compact cometary nucleus should show a smooth, predictable rotation, a simple sinusoidal brightening and dimming, 3I Atlas wrote a jagged, fractured script. Its light curve was characterized by sharp, high-amplitude peaks spiking erratically between uneven valleys, resembling a highly unstable pulse recorded on an alien polygraph. The rotational period was complex, and did not repeat in a simple, single-axis manner. Patterns recurred, but never fully closed, with spikes appearing at strange intervals, confirming that the body was in a state of non-principal axis rotation, or tumbling chaos, a spin around multiple axes simultaneously, unwilling to settle into a stable rhythm. Beyond the fundamental instability, the brightness variations held a second, critical secret: sudden, dramatic bursts of intensity, brief flares that significantly exceeded the magnitude explainable by simple rotation. These specular glints suggested the object was catching the sun at unique angles, acting as a momentary, highly directional mirror. Astronomers immediately debated the implications. Were these reflections from jagged, fractured planes, the raw, polished surfaces left by an ancient interstellar impact? Or did they hint at something deliberately engineered, plate-like shards, or thin, highly reflective material, behaving not as inert rock, but as structured surfaces? The initial shock lay in the sheer violence of the fluctuations, far too extreme for anything so small and so distant. Earth-based telescopes, hampered by atmospheric blur, could only confirm the broadest variation. Mars, however, with its superior clarity and unique phase angle, confirmed the truth. 3I Atlas was not rotating like a compact stone. It was thrashing, flickering, and communicating in bursts of light that defied conventional models. The first light curve, intended as a scientific baseline, instead delivered a fundamental fracture in certainty. Each high-amplitude spike was a question mark, each flare a precise whisper of an unseen, possibly artificial geometry. Following the light curve's erratic script, the expected visual companion, the faint, diffuse coma, entailed trademark of a cometary visitor, remained stubbornly absent. The Mars instruments saw nothing. No expansive coma spread outward, no tail of vapor or dust unfurled behind the object. Yet, despite this stark silence, the orbit was undeniably drifting, its path curving in ways that gravity alone absolutely could not explain. The numbers provided unsettling clarity. Astrometry, meticulously stitched together from high-rise images and confirmed by global ground-based tracking, showed that 3I Atlas was undergoing a measurable, persistent non-gravitational acceleration. This effect, similar to the faint push observed with Oumuamua years earlier, was a force without a visible known cause. Comets generate thrust by shedding supervolatiles, like water or CO, which act as natural thrusters, but under the scrutiny of Mars, no such veil appeared. The paradox was profound. Mars's high-sensitivity spectrometers, which routinely detect trace gases in the planet's own atmosphere, saw no excess CO2 or water vapor surrounding the interloper. Themis thermal readings showed no telltale localized hotspots that would betray the venting of outgassing jets. Maven's plasma sensors recorded disturbances that were too faint and too erratic to explain a steady, sustained thrust. The acceleration remained purely an orbital signature, insistent and undeniable. This contradiction lay at the heart of the mystery, an object behaving as though driven by forces, yet presenting the still, inert face of a barren shard. The required magnitude and directionality of the acceleration exceeded the physical limits of known non-gravitational effects, such as the Yarkovsky effect, by a factor too large to dismiss as error. Some proposed subtle jets of exotic supervolatiles like frozen nitrogen that escaped conventional detection. Others hypothesized the coupling of radiation pressure, with structures too thin for ordinary rock. The acceleration, written silently into the orbital elements, was the central puzzle. It was an acceleration without a visible cause, a motion without a messenger, a secret carried in silence across the solar wind that defied the very laws of passive celestial motion. As the observation days accumulated, the Mars orbiters began to reveal something even stranger than the erratic acceleration. In the hours near local dusk, when sunlight grazed the visitor at extremely shallow angles, HiRISE and CTX recorded precise, needle-like glints, brief, sharp flashes of light. Crucially, these glints did not scatter randomly. They repeated with unnerving, machine-like consistency, as though the object carried specific angled facets turning toward the sun like a mirror array. The light produced was not the broad, diffuse scattering typical of a dusty, irregular surface. It was razor-sharp and, when analyzed, highly polarized, suggesting reflection from incredibly smooth, unblemished surfaces, a feature profoundly rare among natural small bodies. Each glint consistently appeared at nearly the same rotational phase, pointing toward an underlying, rigid, and highly repetitive geometry. The implications were scientifically explosive. While natural shards can glint from fractured ice or polished minerals, the repetition and sharpness spoke of a symmetry too deliberate for mere cosmic chaos. Models run against Mars's unique phase angles suggested that the body was highly non-spheroidal, a long slab-like shape, or a structure riddled with flat, angled concavities. If true, the visitor was less a classic asteroid and more a shard of extreme aspect ratio, a geometry of extremes that unsettled the imagination. The Martian sky, free from atmospheric distortion, provided the only vantage capable of capturing this specificity. Against that stark, clear canvas, the object revealed its flashing secret. Each spike of light cut deeper into the mystery, carrying the scientific unease that the observers were tracking. Not merely stone, but something that knew precisely how to reflect. Something shaped in ways that recalled not random cosmic processes, but structured, possibly intentional, design. Mars, the silent orbiting witness, recorded the glints again and again, reinforcing the growing suspicion that the laws of nature, as currently understood, had been profoundly challenged. Even as the optical teams grappled with the glints, a highly specialized data stream arrived from MAVEN, Mars Atmosphere and Volatile Evolution. MAVEN's primary mission is the study of Mars's tenuous atmosphere and its interaction with the solar wind, meaning its sensors are highly tuned to ions and plasma flows. When 3I Atlas passed through MAVEN's monitoring field, it should have been inert, a silent stone disturbing the solar wind only minimally. Yet, MAVEN detected sudden, distinct flickers in ion density, clear spikes in charge exchange, and irregular, ghost-like currents rippling through the solar plasma flow. These disturbances were meticulously localized in time, matching the predicted intervals when 3I Atlas crossed the observational line of sight. The signals, though faint, were undeniable. A sheath of ionized particles seemed to cling to the object, suggesting it possessed its own coherent plasma envelope. This phenomenon was fundamentally unlike a cometary coma, which is a vast, billowy cloud of ionized water vapor. This sheath was thinner, subtler, and more organized, resembling the charged boundary layer around a highly conductive metallic body, or a structured membrane interacting with the solar wind. Scientists debated in intense, rapid teleconferences. Was this merely static buildup on micron-sized dust grains? Had interstellar radiation baked the object's surface into a highly conductive material? Or could this be evidence of an ultra-thin, extended structure actively interacting with solar particles in ways that passive rocks cannot? The key source of unease was the coherence of the signal. Plasma noise is typically turbulent. Maven's readings showed distinct intervals of order, periodic pulses suggesting a controlled or structured interaction. Mars, by the sheer accident of its orbit and Maven's advanced instrumentation, had captured a feature impossible to see from Earth. The visitor was enveloped in an electric whisper, a plasma veil that was invisible to optical eyes, but entirely tangible to charged particles streaming past, bending the magnetotail like a structured signal from another star system. In parallel with the plasma studies, the spectrometers aboard the ExoMars Trace Gas Orbiter, NOMAD and ACS, provided their confounding chemical analysis. Retuned to scan the faint light of 3I Atlas, the instruments returned data that shattered chemical expectation. The spectral fingerprint of a typical solar system comet is dominated by strong absorption bands for water, CO2, and silicates. In the Mars orbit data, these familiar signatures were either entirely absent or severely distorted. Instead, faint shifting absorption bands appeared, moving subtly from one observation to the next. Initial analysis suggested carbon-bearing molecules, but their intensity and ratio did not align with any known cometary or asteroid chemistry. The possibilities explored were radical, exotic, supervolatile ices like frozen molecular nitrogen or methane, solidified during immense durations of interstellar travel, or tholins, the complex reddish organic polymers forged by the continuous bombardment of cosmic radiation and UV light in deep space, which could explain the reddish tint seen by Earth-based telescopes. However, the Mars instruments revealed the features were dramatically unstable. The spectral bands flared strong in some passes and faded to nothing in others, indicating profound chemical heterogeneity across the body's surface. This variability suggested layered materials, skins of alien chemistry peeling back as the object tumbled, exposing different faces to the sun's light. The spectrum became a patchwork diary of its composition. The shifting bands unnerved theorists because they implied the organics or ices were not uniformly distributed, but possibly concentrated in veins, crusts, or structured sheets. Furthermore, if supervolatiles were present, they were sublimating without producing the dense, visible coma required to explain the orbital acceleration, intensifying the paradox. The data spoke with precision, but the message was confusion. A body layered in strangeness, carrying chemical signatures both familiar and entirely alien. A cipher written by an object older than our sun. The combined anomalies of flickering light curves, sharp glints, and erratic spectra immediately demanded geometric reconstruction. Scientists rapidly employed advanced inversion modeling, feeding the multi-wavelength brightness variations into complex algorithms designed to carve shape from shadow. The resulting form that began to emerge was not the compact spheroid of an asteroid, nor the lumpy snowball of a comet, but something spectacularly elongated, fundamentally improbable, and fractured. The best fit models converged on an object with an extreme aspect ratio, estimated to be at least 10:1, a body stretched thin like a blade or a needle adrift in space. Some iterations revealed deep concavities and scooped depressions designed to catch and reflect sunlight in precise erratic flashes. The most compelling fits hinted at precise flat facets, angled like reflective panels, scattering light in narrow beams consistent with the observed glints. The entire structure was modeled as jagged and non-smooth, a chaotic shard tumbling through the solar system. This result was scientifically revolutionary. First, the elongated slab-like shape is exceptionally rare in nature for kilometer-sized bodies. Collisions typically produce rubble piles or rounded shapes. The required rigidity and extreme slenderness strongly suggested either a completely unknown natural formation process, such as extreme tidal shredding near a supermassive object in its parent system, or a structure designed for purpose. Second, the confirmation of the non-principal axis rotation, tumbling chaos, was now directly linked to the shape. While such motion should naturally dampen over cosmic timescales due to internal friction, the data indicated 3I Atlas had resisted this equilibrium. This required the object to possess an extraordinary internal rigidity, preserving its strange dance. The more the models refined, the more the silhouette resembled not a natural stone, but a highly rigid relic, bearing surfaces and angles that strongly suggested non-random formation. From Mars's vantage, the inversion modeling had completed its task. It turned flicker into an impossible form. What that form revealed was a persistent, unsettling reminder. This visitor carried a geometry too strange to dismiss, a shape that profoundly challenged both science and imagination. If the shape inversion was startling, the thermal data from Themis unsettled the material science teams even more. The instrument's primary task was to trace how 3I Atlas absorbed and released heat as it rotated, measuring its thermal inertia. Here, the visitor broke two distinct sets of expectations simultaneously. A dense rocky asteroid retains heat well, high inertia, warming and cooling slowly. A porous, icy comet heats and cools quickly, low inertia. 3I Atlas refused both categories, exhibiting inconsistent thermal inertia caught in a fundamental paradox. In certain measurements, it cooled far too quickly, behaving like something incredibly fragile, porous, and ultralight. In others, it retained warmth significantly longer than either dust or ice should, suggesting internal layers or hidden pockets that effectively resisted the cold of space. The data hinted at a hybrid, a surface behaving like powdery ash, yet coupled with the internal resilience of a rigid structure. The most advanced comparisons suggested a substance with thermal properties akin to aerogel, a material both ultralight and highly insulating. Compounding this, the acceleration observed earlier had no corresponding thermal signature. If jets were venting, Themis should have seen localized thermal spikes, bright points where sunlight cooked volatile patches into eruption. Instead, the heat patterns were smooth, global, and unbroken by such scarring. The mismatch was a deep fissure in theory, a body that cools like dust but endures like stone, that accelerates without jets, and that carries sharp glints without a coma. This was not the behavior of any familiar solar system body. This thermal anomaly was further refined by the object's emissivity, the measurement of how efficiently its surface shed absorbed infrared energy. The emissivity values were not constant. They slipped and skewed, resisting simple classification. The object radiated heat at times as though it were dark, porous dust, high emissivity. and at other times like smooth, reflective metal, low emissivity. This material heterogeneity, a patchwork of regions alternating between high and low emissivity, suggested a complex mosaic surface, a quilt of materials stitched by violence and time. This mosaic structure, however, also offered a potential mechanism for preserving the chaotic tumble, as differential heat retention would make damping less efficient, allowing the chaotic motion to endure across cosmic timescales. The convergence of the radio whispers and Maven's plasma data gave rise to a powerful theoretical framework, the magnetic drapery hypothesis. The phenomenon is driven by the interaction of the solar wind's magnetic field lines with a non-magnetized obstacle. When the solar wind, an ultra-fast stream of charged particles and embedded magnetic fields, encounters a body, the field lines bend, stretch, and fold around the intruder like fabric caught on a pole, a process known as draping. For most small asteroids, this effect is negligible. For 3I Atlas, however, the draping was subtle but real, a distortion too coherent to ignore. The models suggested something structurally radical. The object's surface must be ultralight, highly conductive, and extended, allowing solar particles to interact with it as though with a wide, conductive foil. In this view, the non-gravitational acceleration observed earlier was not a separate mystery, but a direct consequence of this interaction. The object was being pushed not just by light, photons, but by the momentum transfer from the flow of charged particles, plasma. This interpretation strongly aligned with the radiation sail hypothesis. If the body interacted with light like a sail and with plasma like a conductive foil, the distinction between a natural rock and a highly optimized, fragile structure vanished. The plasma anomalies, which had shown structured, repeating bursts, could be explained by the highly conductive, non-uniform surface rotating through the solar wind, a phenomenon akin to a damaged dynamo or a highly charged capacitor moving through a magnetic field. The magnetic evidence, therefore, served as the ultimate confirmation of the object's profound structural difference. 3. I-Atlas was not a compact boulder adrift in space. It was something wide, thin, and dynamically responsive, a shape made to efficiently couple with the universe's invisible forces. It was a shard that moved as though the solar system itself were its ocean, confirming the object as a dynamic participant in the cosmos, a partner of light and plasma. With the object's paradoxes multiplying, the computational effort turned from theoretical modeling to direct numerical simulation. On Earth, vast supercomputer clusters were tasked with running Monte Carlo campaigns, feeding every scrap of Martian data, light curves, spectra, plasma readings, and emissivity maps, into numerical engines to recreate the observed behavior. At laboratories like JPL and ESA's ESOC, teams varied spin states, material densities, thermal conductivities, and geometries by the tens of thousands. Models incorporating thin, elongated shards with specific reflective facets explained the glints. Thermal models layered with exotic ices could mimic the erratic cooling patterns. But the core frustration remained. No single model captured all features at once. When the model accurately matched the non-gravitational acceleration, it fundamentally broke the spectral or thermal inertia data. Every solution birthed a new, unsolvable contradiction. The time pressure was immense. 3I Atlas was rapidly receding, and the window for close observation was closing. Science was in a desperate race to capture the ghost before it vanished into interstellar silence. The philosophical conclusion that emerged was as significant as any data point. Nature had written an object so layered, so complex, that it stubbornly resisted all mathematical simplification, serving as a profound reminder of the limits of reductionist physics. Even after the instruments were cleared of suspicion, a final, compelling layer of indirect evidence emerged: radio scintillations. Though no dedicated radio telescope had been pointed at the object, the interstellar visitor left faint fingerprints embedded in the background static of deep space communications. Signals relayed between Mars orbiters and Earth. Tight radio beams stretched across millions of kilometers began to waver ever so slightly whenever their path brushed near the body's trajectory. Subtle phase and amplitude fluctuations appeared, as though the signal were passing through a veil of structured plasma. These distortions were sharper and narrower than a typical comet tail, suggesting an organized, compact sheath. Cross-checks with Earth-based VLBI, Very Long Baseline Interferometry, observatories confirmed the effect. Background quasars flickered oddly when their lines of sight aligned with 3I Atlas. The significance was the profound convergence of evidence. Optical instruments showed glints in structure. Plasma detectors registered the electric veil. Now, radio itself, the most faithful cosmic messenger, testified to the same truth. 3 domains: light, particles, and radio. Each independently confirmed the existence of a compact, invisible environment surrounding the object. A halo not born of any ordinary comet. This convergence marked the final turning point. The object was not bare. It was wrapped in a delicate yet real unseen cloak, bending the universe's signals as it passed, hinting at a physics of interstellar passage yet to be understood. The successful, if confounding, campaign around 3I Atlas immediately triggered a massive reevaluation within planetary defense circles. Mars's dual vantage point was recognized as more than a scientific luxury. It was a crucial rehearsal for planetary security. From Earth alone, the object's non-gravitational acceleration was barely measurable noise. From Mars, the contradictions were undeniable, providing the necessary stereo vision to confirm the anomalies. This proved that humanity's future safety against fast, unpredictable interstellar travelers may depend on a two-world observational strategy. A distributed network of observatories scattered across planets, moons, and deep space stations could act as a planetary defense lattice, catching anomalies early and predicting impact risks with a precision impossible from a single vantage point. 3I Atlas became the pivotal case study. Policy papers circulated, arguing that the mystery of its propulsion provided a practical lesson. If orbital mechanics can be defied by unknown forces, humanity must build infrastructure that accounts for non-gravitational uncertainty. Engineers began drafting concrete proposals for relay constellations and small, permanently stationed telescopes around Mars and the Moon, creating a distributed early warning system for cosmic visitors. The Red Planet had become, for a brief moment, not just an observer, but a sentinel. In its patient gaze, humanity glimpsed a new, multi-planetary strategy: to watch the universe together, across worlds, as if the entire solar system were one unified, enormous observatory. Building upon the defense strategy, mission designers moved to the offensive, sketching plans for interstellar interceptors. The frustrating clarity with which 3I Atlas revealed its secrets, only to vanish, provided the necessary urgency. Never again, the voices argued, should humanity let such a messenger slip away without a direct encounter. The challenge was speed and readiness. Interstellar visitors are unbound, moving at high hyperbolic velocities. To catch them, intercept missions must launch almost instantly. Designs included lightweight CubeSats on standby, rapidly deployable solar sails for high acceleration course changes, and advanced ion drives capable of mid-course trajectory adjustments. 3i Atlas provided the clear, quantitative justification for the permanent, poised infrastructure required. The object's anomalies were too rich, too fleeting, and too frustrating to watch vanish. Simultaneously, astronomers looked to the near future and the completion of the Vera C. Rubin Observatory on Earth. Its Large Synoptic Survey Telescope, LSST, promised to turn the occasional sighting of interstellar objects into an abundant, regular inventory. The LSST will sweep the entire observable sky every few nights, cataloging change with relentless cadence, meaning objects like 3i Atlas will be tracked earlier and more precisely than ever before. For planetary defense, Rubin provides the necessary foresight. For interstellar science, it promises abundance, dozens, perhaps hundreds, of enigmas to study over the coming decades. The lesson of 3i Atlas was clear. The object was a riddle too complex for a single vantage to solve. Rubin will cast the net wide from Earth. Mars, with its unique clarity, will be required to tighten it. This two-world, multi-stage strategy, detection by Rubin, high-resolution study by Mars, and potential interception by fast probes, is the enduring legacy of the anomalous visitor. The cosmos had sent a fragment, and soon, humanity would be prepared not only to listen more deeply, but to reach out, with eyes from more than one world. As the weeks passed and the data stream slowed, scientists asked not just what they had seen, but what the experience meant. The final composites from the Mars campaign showed an elongated, tumbling shard, reflecting light in sharp structured flashes. Its surface chemistry was a complex patchwork of radiation scars and exotic organics. Its non-gravitational acceleration spoke of forces too delicate for conventional eyes to see, yet too strong to ignore. Yet through all this, the object never broke its silence. It never unfurled a massive tail, never shed fragments. It slipped through the solar system like a cipher, carrying coherent structure, persistent motion, and profound mystery, but no confession. What did the images whisper? That matter can be arranged in ways we have yet to imagine. That the galaxy forges relics stranger and more resilient than our textbooks dare to describe. That perhaps scattered among the stars are countless such shards, broken, weathered, or perhaps designed, passing silently from system to system, unnoticed until geometry and vigilance align. For the scientists, 3i Atlas became a symbol for the limits of classification and the humility of not knowing. It reminded them that data is not always closure, and that sometimes the universe offers only fragments, glimpses, and provocations. Mars had given humanity its clearest look yet at an interstellar visitor, and in that clarity, paradox deepened. The images whispered not certainty, but infinite wonder. As 3i Atlas drifted beyond Mars's reach, the great campaign that mobilized two planets gradually fell silent, not because the mystery was solved, but because the visitor had simply outrun our instruments. Yet in the stillness that followed, a profound calm settled over the scientific community. They had not unlocked its secrets, but they had proven that worlds can work together. Earth and Mars, separated by millions of kilometers, united in purpose to watch the unknown pass close enough to touch with light. The visitor had become a mirror. In its glints and silences, its plasma whispers and tumbling chaos, it reflected back the truth of our place. Small beings with fragile machines, peering outward with hunger, asking questions larger than ourselves. When the final images were archived, the scientists lingered on them, not as failures, but as reminders. A shard from another star had passed us by, inscrutable, serene, indifferent. Yet it had left us changed. It had forced us to rethink our tools, our models, and our fundamental assumptions about the boundary between natural and engineered objects. Mars had watched in silence, and in that silence, humanity discovered both its limits and its courage. The interstellar visitor moved on, but the questions it raised remained, echoing through observatories, through classrooms, and through the dreams of those who stared into the night sky. The cosmos had spoken in riddles, and though we could not yet solve them, we listened. That, perhaps, was the most profound achievement. And now, as the interstellar shard fades into the black, let us slow our gaze. Imagine the object vanishing into the star fields, its glints no longer sharp, its secrets dissolving into distance. The silence of space enfolds it, and with each passing hour, it becomes less a riddle to solve than a memory to hold. In the hush that follows, we can feel the measure of perspective. Our instruments strained, our theories stretched, and yet what remains is not failure, but wonder. To watch from two worlds, to record light that has traveled across both interstellar void and Martian orbit, is to touch the edge of something vast. And in that touch, humanity is reminded of its place, small, questioning, hopeful. The cosmos does not rush to answer us. Its riddles are not written for quick resolution. They are carved in silence, carried on bodies like 3-eye Atlas, left for us to encounter only in fleeting glimpses. And perhaps that is enough. Perhaps the purpose is not in solving every anomaly, but in learning how to look, how to listen, how to wonder together. So let the visitor drift back into the unknown, its plasma cloak and tumbling shards disappearing into the tapestry of stars. Let the questions it raised linger gently, not as burdens, but as invitations to build better eyes, to keep watch from more than one world, to never stop asking. The night is wide and the sky is deep. As you rest now, imagine Mars still turning in its silence, carrying orbiters that remember, carrying data that endures. Somewhere, 3-eye Atlas sails on, indifferent yet beautiful, leaving us with mystery, leaving us with wonder, leaving us with dreams. The story of 3-eye Atlas is just one thread in the vast tapestry of the cosmos. The universe is full of such mysteries, waiting for those with the curiosity to look. Don't let the wonder end here. Join the Stellify science community. Subscribe and turn on notifications so you can journey with us to the furthest reaches of scientific discovery. Together, we will keep watching, keep questioning, and keep dreaming. Subscribe to Stellify Science now.